Hello and welcome back to Let's Code Physics. We are going to continue looking at our pendulum model today. I'm a little bit more dressed up than last time. I've decided that I need to do my recording in the morning before leaving for work. So I'm a little bit more dressed up than usual, which I'm sure nobody will complain about. So that either means I will have much more energy because I just woke up, or I'll have much less energy depending on how much sleep I got. So you will get to see me what I look like before my students do. Just to recap, we've set up a simple pendulum here. The pendulum is the white construct. The transparent red line is just a reference point for where the pendulum started. Then this, of course, is a graph of the pendulum's angle with respect to time. It's the angle measured from the downward vertical axis here. Although, obviously, if you were to take, the angle from the horizontal, it's just going to be an offset version of that. And then down here, we've got a phase space plot of the pendulum's rotational velocity versus its angle theta. And so that we've seen it approach a limit cycle. So it starts out here at the initial location. It sweeps out this way. It loses some energy due to the drag force, but then the driving force keeps it going in this limit cycle that you see here, this little ellipse. And so what I thought we could do today would be to try out a few different driving force functions, and then in the next episode we'll move to some more complicated and interesting stuff to take a look at, for example, double pendulums or a single pendulum with a movable base. There's some really fun problems. You can get some neat behavior out of those, but we have to go back to the drawing board for the differential equation that describes it. So we'll get to do some Lagrangian mechanics for the first time on this channel, which I'm pretty excited about. So the driving force that resulted in this motion was this cosine function, where we picked a period of 2.5. And now, basically, when you start out with a damped driven pendulum, it starts out with the motion that you would have for the regular pendulum, but the damping force quickly takes away that initial energy that it had, and you end up with just the driving force dominating. So, for example, it doesn't matter what the natural frequency of the pendulum is, which in this case is... All right, so 2 pi square root L over G. L over G is going to be a quarter, so that's a half, so it should be pi. So initially, it's pi that's the sort of special frequency. And you can see at about 3.14 initially, it's about run through a cycle. It's not quite there, again, because of the damping force, but out here, we expect to see a period of 2.5. So between this minimum, we've got a 17.4, and so this one should be 2.5 plus that, a 19.9. Yeah, so we're getting the expected behavior from it. So we've set up Euler-Cromer correctly. Hooray! Wonderful. So what I thought we could do today would be to play around with the driving function, try a few different things. Another thing we tried last time was giving it this kick. So this is where within a certain fraction of the period occurring, so every 2.5 seconds plus or minus 0.1 second, this thing is going to give it a kick of a force of 5, otherwise the force is going to be 0. So this is analogous to when you got a child on a swing, you're not pushing them the entire time, right? This would be an incredibly this original driving function would be an incredibly overactive parent who feels the need to move their child on the swing. This is the more traditional parenting structure, which is the child is going to be swinging, you just give them the kick that they need. Well, sorry, you're not giving them a kick. You give them the boost of energy that the swing needs. There we go. Do not kick your children. I didn't say that. And so what you get is it's similar, right? So initially it starts out kind of like what we had before. So there's a period of about pi, but then there will be a period of about 2.5. So we've got from 13.4 to 15 right about 16. Yeah, that's 2.5. Yeah, right about there is 2.5. Only it's got this cusp right here, and you can see it even more dramatically in the phase space plot, because that's where it's giving the kick. That's where the kick is happening. Let's actually let this thing run for longer. See, our Tmax was 20. Let's go ahead and make this be while true. It's a neat trick. It takes my students a couple weeks or so to figure out what that trick means. And I say, well, for how long is true true? And they say, well, always. I say, okay, so it's going to keep running. And yeah, so you get this. I wish I had a stop button. I guess that's what I need to build into this thing. So you get this nice little behavior there. Maybe I should put in a Tmax. So you get this cool behavior. What I thought might be fun to try, and let's go ahead and increase the Tmax to say 50. What I thought might be fun to try. So this thing has a natural frequency of about pi, of about 3.14. And this is relatively close to that. What I thought might be interesting would be to see what happens when we make this thing's period be half of pi. So we take 3.14, divide it by 2, because then what's happening is, so the natural frequency is going to be to go from this side to this side in pi. So if you made the kick at pi, actually let's make the kick at pi. If you make the kick at pi, then you are pushing the child right when they are coming back. So the push is happening right when the pendulum comes over to this way. And you get this nice sort of maximum motion there, because any parent will tell you that's the time where you push the swing, is when it comes back this way. Let's see if we can visualize that a little bit better. I'm going to decrease the rate of the animation. There we go. So every pi seconds there will be a kick. So there's a kick. You can see the little discontinuity there. And there's the kick. So it's not quite matching up. So I suppose I can use I can be a bit more accurate with that. Actually, I think Python knows pi. Let's find out. I think it's %pi. Is that right? Let's find out. Nope, it does not like that. Okay. No, I'm thinking of MATLAB. Okay. Well, let's make it easy on ourselves rather than trying to. No, not Pinterest. Pi. There we go. We'll just copy and paste. There we go. Actually, let's call it pi. Let's go ahead and define pi up here. Pi equals. No, that is not what I wanted. That's a bit bizarre. Okay. All right, we'll leave off the 9 there. Paste. There we go. I think I was accidentally copying some of the calculator there. Okay. So we'll make the period pi, and so it's the kick is going to naturally line up with when the pendulum swings over to here. But of course, there's a damping force. The damping force is elongating the period just a little bit. So we're getting a kick this way. You can see the kink moving on here. It's kind of interesting because it's not quite matching up with the natural frequency. Let's see. I don't want to get rid of the damping force, but I can decrease it a little bit. And kick. Okay, yeah, so it gets the kick sort of right before it reaches there. Kick. Okay, so you notice we're actually gaining some energy because the pendulum bob is going past the initial line, which you can also see by the increasing amplitude here. So we are adding some energy to this thing. It looks like we are losing some energy now, so we're not quite matching up with this, not quite reaching here. You can also tell that by the radius of this ellipse. I know ellipses have 2 radii, but they're different units anyway. You can tell this by the broadness of the ellipse. You can also see that the kink is happening at different locations around here, so that's kind of cool. So that's producing some pretty good behavior. That's producing some nice, that's some nice constructive input. But what happens if we make this period pi divided by 2? So in other words, this is the kid gets to the other side of the swing, and that's when you as a parent decide, oh, I think I'll push him this way. That's not good swinging or good parenting. Let's see what it looks like on the graph. So you get a kick here. Going to get a kick there. Okay, so you see this thing is not quite working out right. I mean, we're still getting the sinusoidal motion. But if we watch this, So you see, now we're getting a kink on this side and a kink on this side. Before we were getting one or the other, but now we're getting 2 kinks per cycle. And you can see the motion is dying down pretty quickly, right? Because you're pushing the kid at the wrong time. I suppose another way we could do this would be, I hadn't thought about this before. This is a function of theta, theta dot and time. So I suppose another way to do this, let's comment these out, would be make the condition based on the location of the swing instead of on the time. So in other words, let's see, how do I want to do that? I want to do it whenever theta dot is equal to 0. So if theta dot is less than, what should the tolerance be? I should have taken a look at the values we were getting there. Let's see, what kind of values are we getting for theta dot here? Oh, whoops, I need to define FD, excuse me. We'll just have a FD equals 0 there for safety's sake. What kind of values are we getting for theta dot? Okay, so we're getting on the order of 1.5%. Okay, so a 0.1 ought to be enough, because that's like this region right here. Okay, so here's what I'm thinking. What if you push every time theta dot is equal to 0.1? Or is less than, is within negative 0.1 and 0.1. Okay, so we're going to say if absolute value of theta dot is less than 0.1. So whenever it's within that little window, that's when you push. FD equals, let's stick with the 5. And then we'll say else FD equals 0.0. And we can comment this out just so it's one fewer calculation steps. Let me make a note to myself here. Uncomment if you're taking out driving force. There we go. So this now is going to look for every time theta dot equals 0. But of course that's happening twice. It's happening over at the right side and at the left side. So we could put in an and here if theta is greater than 0. Right, so this would be the right way to do it. This is only when it comes over to one side. Let's see what we get here. Oh, right, it starts out like that, and so this thing is pushing it up this way. Oops, I didn't think about that. Okay, and time greater than 0. Let's say time greater than 1. The things you don't think about, huh? All right. Okay, there we go. Now it'll make it through one cycle, and now we get a kick. That's not a very good kick. Oh, I need to have it kick the other way. Oh, in fact, I wonder if that's been a problem the whole time. That I need it to be a -5 because I want it to go clockwise. Clocks are negative, so that needs to be a negative there. Oops. And kick it back. Okay, there we go. Now we're pushing the child correctly. Oh, gosh, did I do that wrong in the last video? Okay, well, redaction to the last video, that should have been a -5. Oh, well. So this is, the swing is coming up and the parent is pulling the kid up. Which I suppose is not a bad way to do it. That might be worth trying sometime. I don't know. Okay, so the amplitudes have definitely died down. This thing is continuing to spiral inward. We might be getting... no. Oh, you know what? It's probably going to spiral until we get really close to 0.1 would be my guess. Yeah, if you look, it's getting... the distance between each cycle is decreasing. Okay, so the question is the distance between each cycle decreasing enough to where it will limit cycle out? And of course, we don't get to see that. Yeah, here's where the kick is happening there. Okay, cool. All right, so let's see what happens. And of course, that'll get a little bit better. I think that'll get a little bit better if we make the kick stronger. And kick. Okay, awesome, cool. Yeah, you can see the discontinuity starting to show up there. And basically that discontinuity is within the range of 0.1, which is pretty cool. Okay, so let's take out this part now. Because if I take out that theta greater than 0, copy, paste. If I take out that theta greater than 0, then this is going to be the parent who decides to push here and push in the same direction on the other side. All right. So they're going to push here. Oh, and it's continuing to push because the speed is still within that range. Okay, so I haven't quite set up the condition correctly there. Because this is somebody continuing to push around this way. All right, let's try it a little bit differently. Let's try multiplying this by the sine of theta. You don't know sine, do you? SGN? No? Okay. So, in other words, let's say you push to the right, let's say you push to the left when they're on the right side, and you push to the left when they're, to the right when they're on the left side. So the way you can, so if your programming language doesn't know the sine function, SIGN, it's easy to get. You just take the value theta and divide it by theta dot, or excuse me, divide it by absolute value theta. There we go. Of course, that'll be a problem if the thing is 0. So let's say and theta, absolute value of theta greater than 0.1. There we go. So this is going to be, so this is you've got two parents, one on either side, pushing the kid, or a parent and a babysitter, you know. So you get a kick there, and you get a kick there. And of course, that works out a little bit better because you're getting energy into the system more regularly. Which is cool. Okay. All right, so I think we've had enough fun with the kicks. We'll leave that in for future reference. Let's try some other driving functions. Let's see, what did I want to try next? Let's try, let's see, we get kick with half the natural frequency. Let's try the Sawtooth function. So the Sawtooth function is interesting. This is where you've got this linear function going like this. So let's see. So let's say we've got our period of, let's take our period to be pi over 2 again. Yeah, let's take that one. And let's work kind of the similar thing that we've got here. So if, oops, no, I need to indent. If the absolute value of time with the period is, okay, so we want this to be, let's see, we want for half of it to be going up and the other half of it to be going down, right? So I'm probably going to end up needing to graph the driving force to make sure that I'm doing what I think I'm doing. Hello, Miss Pumpkin. It's so good to see you. Everybody wish Pumpkin a happy birthday. We are recording this on her birthday, and she just got her monthly flea medicine, so she's usually a little bit skittish. So let's see. Oh, I need to close that up anyway. So the absolute value of time with the of modulus of time with the period is, let's say, I think the way I can do this is say greater than period over 2, right? Because the modulus is going to range from 0 to period. Then let's have it do this. And I might need to flip that from a greater than to a less than sign. So I need this to be linear. Oh goodness, I should have looked up how to encode the Sawtooth function. Sawtooth function, there we go. All right, let's go with Wolfram alpha. Oh, I just used the frac function, the fractional part. A is the amplitude. Oh, that's not even what I wanted anyway. I wanted it to be going like this, up and down. Okay. Well, I tell you what, let's not worry about that one because that's going to be more or less the same type of thing. Let's try the step function. So the step function is interesting. Okay, why don't we cut out that whole Sawtooth business? So one of the functions we can try is the step function. This is where you've got a force coming in and then no force, and then you got a force coming in and then no force. So it's I suppose that's basically what we had for the. Okay, let's cut that again. So we can actually modify this kick function into the step function. Let's leave that hashed out. The step function is basically the same thing, except we're just going to broaden this part out to where it's putting out the force for half of the period, so period over 2. So you'll have a constant force for, let's see, half of pi is like 0.75 or something. Yeah, 3/4. And so you'll have force and then no force, and then you have force and then no force. Okay, I'm thinking I need to add in for visualization's sake, let's add in a graph of the driving force function. Let's see, how do I want to do that? I think, well, obviously I need to create a new G curve. So let's have a G display. Where can that one go? Let's try to get that one in here-ish. So let's say x equals 200, y equals 400. Because I can't really have that on the same graph as any of my other. I mean, I can, but they have different units, so I couldn't live with myself if I did that. Sorry. FD versus time is going to be a G curve with color equal color dot, and let's make this one, let's make it white just for distinguishing's sake. And then we'll have down here a FD versus time dot plot position. And this will be time and FD. This will just help us visualize when the kicks are happening. G-idsplay. G-idsplay. Gidsplay. Okay, so there we get a kick. All right, there we get it. There we don't. Okay, so that's interesting because sometimes it results in a max and sometimes it results in a min. So that's kind of cool. And basically we end up with this shape on the phase space plot. Let's see if we can align this with something. So there's a kick. There's no kick. Okay, yeah, so there's going to be a change whenever there's a cusp on one of these things. And you look at this for a while, and I mean, it's definitely tracing out the same pattern, but I don't know that it's going back around on itself. So that's interesting. This is also the type of thing that's interesting to look at to see how it's affected by the initial conditions, because then we can end up with, we can end up seeing whether we've got chaotic motion, because chaotic motion, has this drastic change based on the initial conditions. So that's interesting. So that's what our current initial conditions look like. Let's try changing the initial theta. Let's try cutting that in half. See if we get something different looking. Okay, we're still getting the same kind of little, it almost looks like, this looks like what in my head tying my shoes feels like, is looping and sudden changes in direction of force and everything. But it's looking more or less like the same pattern, so that's cool. I don't think you get to see chaotic motion with a single pendulum. I think you have to go to a double pendulum for that. I could be wrong about that. Please, if there is an example of a chaotic single pendulum, let me know. But I think you have to go to double for chaotic motion. Yeah, I'm thinking we're seeing the same type of thing there. We can try one other thing though, and that's changing the initial theta dot. Let's have this thing going in the negative direction at first. We can make, yeah, 0.25 ought to be fine. So now it's going to be swinging down first, but then it gets pushed back. So that doesn't make too big a difference. Oh, we get a little loop there. I don't think we had that type of thing before in the middle, did we? I suppose I should be screenshotting these, huh? Well, you can go back on the video and you can, pause the screen and compare and, if you're in school, you can write an entire paper on this behavior if you cite your sources, or better yet, you can download the code from the description below and work with it yourself. Yeah, this is giving basically the same type of behavior. But let's put it back. Do we get that loop in the middle? I don't remember seeing that. -0 is still 0. Oh, we don't. It's a cusp right there in the middle, it looks like. Yeah, that's a cusp right there. Okay, so now what I'm interested in is what do I have to do to this thing to make the loop appear in the middle? So I can change values of the initial speed, not really getting it there. I suppose I can, no, let's leave it running. 0.05 maybe? Because that's interesting, right? Because that's a change in the qualitative behavior. Okay, so that was interesting because that one shot it above the horizontal axis, but I'm not getting the loop there on that first cusp. Let's try -0.1. So basically what you would look for here would be the critical value at which the loop-de-loop appears. Okay, so it's somewhere between -0.05 and -0.1. So you just keep splitting the difference, and basically what you would do in a study of this is keep splitting the difference until you find that loop-de-loop. Or better yet, you figure out a way for the computer to recognize the loop-de-loop, and you have it iterate forward until it finds it. All right, but I'm going to change this thing's Tmax to be smaller than that because I only want it to get to right about there. Okay, yeah, that ought to be perfect. Okay, so I'm getting the eye of the needle there. So I was getting it for 0.1, so let's try 0.08. So we will try to hunt down this critical value, and then we'll call it a day, I think, because I got to get to work. Let's try 0.09. Oh, no, wait, I need to split the difference the other way, excuse me. 0.0, was it present at 0.075? I just realized I did that wrong. Another reason why it's better to have the computer do it. 0.075. Okay, yeah, I needed to go the other way, excuse me. I need to go like to 0.06. Because it wasn't showing up at -0.05. It's showing up there. Let me double check -0.05 because you're all laughing at me, I'm sure. Not laughing, I'm sure y'all don't laugh at me. You might scream at your screen. Oh, it is showing up. It's just really small. And of course, I still haven't figured out how to drag within this thing. Okay. So let's try because it wasn't happening at 0.01, right? Or maybe it is and it's just small, right? So that's another thing you have to look for is what happens if I change the time step value. I don't think it's going to happen till after it passes the horizontal axis there. Let's try 0.02. So it's crossing the horizontal axis, but it's kind of hard to tell whether there's a loop. So actually, let's change our DT. This is going to run half as slow now. Let's see what difference we get there. Oh, it's arcing so much more gracefully now until it gets the kick. Okay. Yeah, so it's being pretty consistent. Okay, well, that's something to play around with, see if you can find the critical value. Another fun thing we can do is instead of having it go from 5 to 0, we can have it go from 5 to -5. So this is sort of there's square wave, and then there's square wave that has a bottom of 0, and square wave that's split across 0. So this is actually fun to do. And then I think we'll call it a day. And so you see now what you're getting is you're getting a +5 and then a -5, and a +5 and a -5, and it makes a little bit different shape. Let's put the Tmax back up, my bad. So we will watch this. So the next thing I'm going to do, I'll do a little bit of work off camera, working out my Lagrangian mechanics for a double pendulum and a pendulum with a movable base here. And then we'll start animating some more interesting stuff. Because there's some neat stuff you can do where you have this thing on a movable track, and you have the pendulum vertical, and you can actually work it out to where the pendulum stays vertical. It's really cool. Okay, so we're getting more or less the same type of behavior. It'll have like a different, range and everything of values on the phase space graph, but we're getting more or less the same thing, and it's continuing to, trace out the same type of shape. So if there is, yes, I don't know if you would call this a limit cycle because it keeps tracing back around, but this thing is definitely, showing some kind of pattern. So you'd have to let this run a bit longer to see the limit cycle. So anyway, this is some interesting stuff. I love me some good phase space first thing in the morning. I think we'll see it'll trace itself back, but then it'll go somewhere it hasn't gone before. So that's kind of cool. So anyway, thank you so much for watching. I will see you next time. Have a great day. Bye-bye.